Gentlemen, welcome to Irvine Barclay Theater. We would like to remind you that photography or video recording is not permitted. In consideration of others, all phones and other electronic devices should be turned to silent mode. Also, please take a moment to note the emergency exits in your seating area. Thank you and enjoy the performance.
So good evening. I'm Peter Taborek. I'm the chair of the Department of Physics and Astronomy here at UCI. And I have the honor and privilege of welcoming you to the first Rhinus lecture. And before we get on with that, I'd like to give you some background on the impact that Frederick Rhinus had both on science and on the history and development of the department at UCI. In 1995, UCI was electrified with the announcement that two of our faculty had gotten the Nobel Prize. One was in chemistry to Sherwood Rowland, and the other one was to Frederick Rhinus. Rhinus's Nobel Prize was for the first detection of a neutrino, which in our modern understanding is one of the basic building blocks of the entire universe. Neutrinos are extremely weakly interacting and hard to detect. This room has billions of them flying through the room, and I bet you haven't noticed. In fact, you may have heard that neutrinos can go through the entire Earth without interacting, and that is, in fact, true. The theorists who predicted the existence of this particle in the 30s thought that it was so weakly interacting that it was going to be undetectable, and that was a challenge that Rhinus couldn't resist. He took it up and attempted to make a detector that could see it, and the first detector was a specialized device that worked at a nuclear reactor to detect the neutrinos. And that's the experiment that he got the Nobel Prize for. Today, the study of neutrinos is an industry with thousands of physicists all over the world working on various problems associated with them. Rhinus got the Nobel Prize for discovering the neutrino, but he did several other very significant scientific accomplishments. He became an expert in and sort of a champion of the idea of building extremely large detectors, usually in mines, so that they would filter out all the other background particles. One of his detectors was in a mine in South Africa, and it was the first to detect neutrinos coming from the atmosphere. And if you think about that for a minute, the neutrinos actually had to go through the Earth. It's a detector that looks downward through the Earth. On February 23rd, 1987, they made another discovery, and this was in a detector that was outside of Cleveland, and it was a truly remarkable thing. It was the detection of neutrinos from outside our galaxy. And if you think about this for a minute, it was really amazing. A star blew up 168,000 years ago. Neutrinos flew through space, entered a detector, and a bunch of physicists sitting in the bottom of a salt mine somewhere outside Cleveland saw about 20 neutrinos entering their detector, and that detector is about the size of this building. And those were the first neutrinos that we have ever seen from outside of our galaxy. And that event was the start of an entire new field, which is neutrino astronomy, and that's something that UCI still has a very strong position in. Rhinus was also a great academic administrator. And in 1966, he took up the challenge of coming to school and took up the challenge of building a department from the ground up. And he was the first dean of the School of Physical Sciences here at UCI. From that beginning, the School of Physical Sciences now has 140 faculty, 1,200 undergraduate students, about 400 graduate students earning degrees in chemistry, earth system science, mathematics, and physics and astronomy. The school's graduated thousands of alumni, and we're especially delighted to welcome so many of our distinguished alumni from the UCI Department of Physics and Astronomy who are here tonight. If you are a member of the UCI family, you are probably aware that UCI was ranked as the #1 university in the United States under the age of 50. This was a great honor, and it's a testament to the high quality both of our faculty and our alumni. This year is UCI's 50th anniversary, and so on next year's rankings, we graduate from the 50 and under category and have to compete with all the best universities in the world. We've had an internal discussion about how to do that. And the challenges of running a great public university have changed significantly in the last 50 years. In the era when Fred Reines was making his discoveries, public universities were supported by the public. If you've read the newspapers or perhaps written a tuition check, you know that this is no longer true. In this time of budget cuts and sequestration, tax funds support about 20% of UCI's cost, and successful public universities will necessarily rely more and more on philanthropy, just like private universities do. The issues that we in physics and astronomy work on are often very long-range projects. Tonight you will hear about neutrinos and quarks and dark matter. Research in these subjects does not lead to immediate commercialization of cool gizmos or cures for disease, although the foundations of that kind of work it stems from exactly that kind of work. Our type of science asks fundamental questions about the universe and how we fit into it. We invite you all to participate in answering these big questions and solving the world's big problems through your support of the UCI Physics and Astronomy Fellowship Fund. You'll find more information on opportunities as you leave the theater this evening, and I thank you on the behalf of the Department of Physics and Astronomy for your support. At this time, I'd like to introduce my colleague, Professor Jonathan Feng, who will give you some remarks about tonight's speaker.
Well, good evening, and let me also welcome you. Thank you for coming. It's my pleasure to introduce our speaker for tonight, Professor Frank Wilczek, the Hermann Feshbach Professor of Physics at MIT. Professor Wilczek's early career is the stuff of legend in academic circles. In physics, the correct description of the forces through which particles interact with each other is absolutely central. Among the great achievements in science are the description of the gravitational force by Isaac Newton, and later, in a more refined form, by Albert Einstein. Similarly, the forces of electricity and magnetism, as you all know, were well described through the work of many people, but culminating in the beautiful synthesis of James Clerk Maxwell in the late 1800s. In 1973, as a 21-year-old graduate student at Princeton University, Professor Wilczek added to this canon by correctly describing a new force known as the strong force. In these papers, Frank and his advisor, David Gross, showed how the strong force holds quarks together to form protons, and protons and neutrons together to form atomic nuclei. This theory has now been tested thousands of times by various experiments, precise experiments, emerging victorious every time, and is one of the pillars of our current understanding of matter and its interactions. Following those papers, Frank made contributions in a wide variety of fields. In a time when most researchers specialize to a very high degree, Frank has remained one of the world's most versatile and broad researchers, making fundamental contributions in particle physics, which is the study of nature's fundamental building blocks, in condensed matter physics, the study of materials, and in cosmology, the study of the universe as a whole on the largest length scales imaginable. For his contributions, Frank has received a host of honorary degrees and awards, far too many to mention here, but including the Nobel Prize in Physics in 2004. Remarkably, Frank has at the same time also devoted a considerable amount of effort to explaining topics at the frontiers of physics to general audiences. In 2003, he received the Lilienfeld Prize of the American Physical Society for, quote, his outstanding ability to lecture and write with clarity, profundity, and enthusiasm, end quote. His books include Longing for the Harmonies, Fantastic Realities, and The Lightness of Being, which you can find in the lobby tonight, and also one which is in progress and which we will get a short preview of in the talk tonight. Casey Cole, who was well known to many of us in Southern California for her writings on science in the LA Times, wrote that reading Frank's books, and I quote here, is almost as much fun as hanging around Frank Wilczek, a feast of continual surprise and insight from a mischievous physics mensch who always has a twinkle in his eye, sees everything new, and never ever says what you expect. Whatever you thought you ever knew about physics suddenly gets a whole lot more interesting. So please join me in welcoming our inaugural Reines lecturer, Frank Wilczek.
Thank you, Jonathan. Thank you, Professor Tabarrok. It's a great honor to be the inaugural Reines lecturer. Professor Tabarrok has explained to you Rhinus's achievements, we'll see that neutrinos continue to be a very central part of our fundamental understanding of the world. They'll play a big role towards the end of this talk. My topic tonight is a single question, a beautiful question. This question: does the world embody beautiful ideas? We'll see that many different styles of thinking have addressed this question, enriched our understanding of what it means, and lead to a remarkable answer. Let me start by describing a crossroads of art and science, that is the concepts of perspective and symmetry. I've struggled, and I think finally succeeded to a certain extent, in making the sometimes esoteric concepts of fundamental physics visual and things that people can relate to and experience in their own lives, even without elaborate training. So, what is perspective, and what does it have to do with symmetry and the way we think about fundamental law? Well, if you study geometry, ordinarily you're taught that parallel lines never meet, and if you look at train tracks on a flat surface of the earth, they don't, and look from the top, you'll see that they look like parallels, they don't meet. However, there's another way of looking at it. And here we see very clearly with our own eyeballs that they do meet. This leads to a very profound and fruitful question. What transformations can one make on an image while representing the same thing, just viewed from different vantage points? That question leads to the science or the art of perspective in the study of art, and the same subject is called projective geometry in mathematics. It's a very beautiful subject. I wish my geometry classes had started with this. I won't go through the construction, but there's a very beautiful construction that will enable you, just using a ruler, to make the appearance of a tiled floor that's tiled with squares. So it's a very rigorous construction that tells you how things can look. The Renaissance artists who made these discoveries, and it was artists before mathematicians or scientists who did it, obviously took great delight in it, and you can see the exuberance, the joy, and the mastery that was achieved in a very short time. The insight, then, is that many different perspectives can represent the same content. This idea that you can represent the same thing while making transformations is the concept of symmetry, the mathematical concept of symmetry that we use in physics. We use it, however, not as symmetry of images, transforms of images, but to make transformations of our fundamental equations, our laws of physics. It may seem far-fetched, but it's absolutely true, Jonathan will vouch for this, that the way we construct our deepest theories of nature is by demanding that our equations can support lots of different ways of being written, all of which lead to the same consequences. So they represent the same underlying reality from different vantage points. And if we allow ourselves enough different ways of looking at things and demand that our equations always, after those transformations, represent the same content, very special equations. Okay? Most equations, if you transform them, change your x's into y's and your y's into z's and so forth, they won't have the same consequences, but very special equations that, for instance, represent the view of the world that's appropriate to people moving past each other at constant velocity in the special theory of relativity. Those lead to very different viewpoints, very different equations, but according to Einstein's special relativity, they have the same content. That is special relativity. And leads us to very specific equations. Now, we go beyond special relativity by a seemingly bold, well, definitely bold, seemingly bizarre extension of the idea of perspective, where perspective goes local. Perspective was changing viewpoints, looking at different ways of things, of recognizing and recognizing the same image. I mean, changing the image and recognizing that it's still the same thing. If you allow larger classes of transformations, like this, if you want to say that this is still the same thing, up there, then it involves more than just looking from a different point of view. If you want to make such bold transformations that distort things, that change things, change the look of things, their shape, you need a medium, you need some enabling device that lets it happen. To allow more general symmetry, more this generalized concept of different perspectives giving the same object, we have to allow for the existence of media, materials that can be responsible for the changes. Now, in the theory of general relativity, this medium is called the metric fluid. It tells us how space and time are organized so that distorted images measured with appropriate rulers and clocks in space-time can represent the same underlying reality. And the yoga of general relativity in a nutshell, that profound theory of how gravity works, is this. The metric fluid tells matter. The metric fluid becomes an actual fluid. The enabling material in a sense, becomes substantial. The metric fluid tells matter, that is, energy and momentum, how to move. And energy and momentum, in turn, tells the metric fluid how to flow. John Wheeler gave an early version of this concept. He said, matter tells space-time how to curve, and space-time tells matter how to move. But I want it to be a little bit more precise because, as you'll see, we're going to use a very similar kind of yoga, not only for gravity, but for all the other forces. But to do that, I'm sorry. First, let me present an image of how we construct theories. It's very much the way artists construct their anamorphic images. So this is the art of theory construction. You specify what substance is that you want to incorporate in your world description. You choose what perspectives you're going to allow, what generalized notion of perspective you're going to allow, to say that these different, very different looking representations really represent the same thing. And then you have to design the enabling material that allows those transformations. So that was an image of what an artist does, but what a physicist does is exactly the same thing. Okay, now, to get from gravity to the other interactions, I have to discuss something that you're all familiar with, but I'll show you some different ways of looking at it that I think you'll find informative and lead in to our deep theories of the other forces. So, color. This is James Clerk Maxwell, who was mentioned earlier, the great theoretical physicist of the 19th century who developed our modern understanding of electricity and magnetism and the nature of light as an electromagnetic disturbance. This is Maxwell as a young man, and he's got some strange thing in his hand there. What is that? This is a so-called color top, and using that kind of thing, that toy-like device, Maxwell elucidated the nature of our perception of color. So he not only got the theory of light, what it is physically, but also the very profoundly different idea of how we sense it. So this is the kind of thing that would be on a color top. You have two rings, and the rings have different colored papers. And when you twirl it around, if you twirl it fast, because of the persistence of vision, you get mixtures of the colors. And what Maxwell did in a very elaborate set of experiments that took, that he indulged in over his whole scientific career, he wrote more papers on this subject than on electricity and magnetism. He showed that you could match any color on the outside, so you could twirl and then see if the colors seem to match. You can match any color on the outside using mixtures of three given colors on the inside. So much later, people realized that this is because our sense of vision is based on three kinds of proteins that respond to different spectral ranges of colors. But at the time, it was just a physiological, perceptual experiment. So Maxwell, in this way, just founded the theory of color that enables us to make arbitrary colors, for instance, in computer displays or in televisions, by using just three different kinds of lights, and in suitable mixtures, they'll make any other perceived kind of light. So you can make yellow in a very different way than the yellow of the rainbow. This is by mixing green and red. You can mix rainbow red and rainbow green to make yellow, which is a mixture, not the pure yellow, and so forth. Now, People have been very fond of speculating about extra dimensions. What would it be like to live in extra dimensions? Very mysterious, very hard to imagine. Actually, it's not. Every time you look, so here's a kind of abstract picture of extra dimensions. Okay, they have a two-dimensional space and then little extra dimensions where you can move if the physical world had extra dimensions. This is a color cube. This was representing Maxwell's insight that by mixing 3 different pure colors, you can generate any perceived color. So you need 3 directions in which to have intensities of colors, and then you get a cube which represents all possible perceived colors. Now, remember this picture? Remember that picture? And now take a look at this one. Every time you look at a computer screen, the different pixels are choices of places in this color cube. So you're you're seeing extra dimensions. And if you ask a computer, or if you want to tell a computer what to do, what to output on its screen, you have to tell it at a given point, X and Y, at a time T, how much red, how much green, and how much blue should there be. And you see in this representation, the R and the G and the B look very much like the X, Y, and T, and so it really is extra dimensions. Now, so that's what extra dimensions look like. Just now, remember, I talked about anamorphic art, where you consider a generalized notion of perspective, where you allow deformations of space by having an appropriate media, or deformations of look of things by allowing appropriate media. You can do a similar trick, it turns out, in our fundamental theories of the other forces. That's because the concepts of those other forces they're based on a generalization of the concept of electric charge. So electric charge is the basis of electromagnetism. The electromagnetic photon field is set up by the position and motion of charges and influences those. It sounds very Wheeleristic, and it will sound more Wheeleristic as I develop it. It turns out that our fundamental theories of the weak and strong interactions, the other interactions that figure into the deep laws of nature, are sort of like electricity and magnetism on steroids. They're based on the same kind of concept of charge, but instead of having just one kind of charge, like in electromagnetism, in the weak interactions you have 2, and in the strong interactions you have 3. Together with that comes in the weak interactions, instead of having just one photon, you have 3. And in QCD, the theory of the strong interactions, instead of just one photon, you have 8. 8 different kinds of photons that can change or respond to the different charges, 3 different charges that we have in the strong interactions in quantum chromodynamics. Now, amazingly, the word we use for these charges in QCD is color. And what's amazing about it is we have three colors, so it maps on exactly to our perception of color. I don't know, maybe that's evidence that God exists or something, but anyway. The misuse of the word of color in describing these charges turns out to be actually prescient. So here is this idea that different amounts of charge are embodied in the different interactions, different numbers of charge, different dimensions of the color cube, if you like. But now it's not representing perceptual colors, but different amounts of charges. In the electromagnetic interactions, we have just one kind. So it's just green here, different shades of green. This one is lacking blue, so it has red and green. It's a two-dimensional color space. And then when we finally come to QCD, quantum chromodynamics, we have the full three-dimensional color space. And that's why this is the nicest interaction. Now, remember, I've said that the driving idea of general relativity is that we want to allow, want to have equations that allow very, very large classes of transformations that leave their content the same. So, like anamorphic changes in the structure of space. If you think that's changing images is changing the structure of space. Now we have new spaces associated with the new charges, so those color spaces sitting over space. We can ask, can we make wild transformations in those spaces and with appropriate media have equations that retain the same content? Here's a picture of the kind of not anamorphic, not changes in shape, but changes in color transformations that we want to be allowed and still have all these things represent the same underlying reality. So here's an original picture of a candy stall in Barcelona. You can change the colors towards the blue so that you get this one. But you can also make the more general kind of transformations where you change the color in different ways at different places. Then you get something like this, something like this. And if you want to have a medium that you can look through so that this will look like that and look like that, the medium has to have very specific properties. That now is not the metric fluid, but the gluon fluid, the fluid that the gluons provide. The color gluons of the strong interaction. So in electromagnetism, to allow these kinds of local changes in the colors, the one-dimensional color space, we have to introduce a photon field. In the weak interactions, we have to introduce the weak-on field. And in the strong interactions, the color gluon field, or also called fluid. The yoga of QED, once you think about this way, quantum electrodynamics, the electrodynamics of one kind of electric charge, is that the electromagnetic photon fluid tells matter how to move. Matter in its aspect of being something that carries electric charge. So remember, general relativity cared about the energy and momentum of matter, but our fundamental understanding says that matter has other properties, including electric and color charges, and they also play very parallel but different role because they have their own fluids that influence their motion and whose structure they influence. So the electromagnetic photon field fluid tells matter how to move, and electric charge tells the photon fluid how to flow. Sounds very much like the theory of gravity. And in fact, the way we construct those theories is very, very similar. And the yoga of QCD, the gluon fluid tells matter in its aspect of color charge how to move, and the color charge tells the gluon field how to flow. And I'll leave it as an exercise to you to formulate the yoga of the weak interaction. The upshot of all this is that gravitons, photons, color gluons, weakons, all those force-carrying entities, those force-carrying fluids, are things that enable symmetry, and their existence is a reflection of the symmetry you want to enable. So, to our deepest understanding, the existence of all these things and all their properties flow from that conceptual function. Now, I recently took a trip to China and I learned something shocking. The yin-yang, that's not what this means. This means two fish. And a wonderful modern master of traditional Chinese art wanted to instruct me and knew that I was interested in these things, so he produced a beautiful image of this kind. Let me first show it, and then I'll circle back. There's the image, and you see, now it looks like two fish when properly drawn. So here's where we left off, our description of the fundamental interactions. So people found these concepts beautiful before they knew that they govern the fundamental laws of physics. That is, specifically, that you have something that's a force and something that's a substance, and the force moves the substance molds the force. This is the essence of Taiji or yin-yang, and according to Xu Fahe, who was the artist here, what this is saying is that Taiji, or two fish, is the essence of Chinese culture, and very obviously meant by them to embody deep beauty. So, in the philosophy that goes with these, that's behind this symbol, yin is substance, yang is force. Each responds to and is shaped by the other. And notice these eyes. Each contains an aspect of the other. Now, again, this is eerily reminiscent of our concepts in physics. The substance can also by being exchanged as virtual particles lead to forces. The forces also involve particles or substance. The photon is a real particle as well as something that mediates a force. So all of them have this dual aspect. So remember our question, does the world embody beautiful ideas? We're getting there. We're getting to an answer. but let me show you something else. So the concept of interplay of force and substance is something that people had thought about before and profoundly internalized. How about the other big ideas that I mentioned? The principles of anamorphic and anachromic art. These principles that it's beautiful to be able to change the shape of things, and it's beautiful to be able to modulate their colors. Well, look at this. You see this extraordinary image of the Grand Mosque in Iran, the local structure of colors, a sort of sublime version of that silly photograph I showed you of the candy stall in Barcelona, and the wonderful shape-shifting as well as color shifting clearly makes this a stunning object. So, coming back to our question, does the world embody beautiful ideas? Yes. Beauty of concept, the interplay of force and substance, beauty of form, the anamorphic aspect, and last but not least, beauty of color. So that's physics today. We've learned, physicists have learned that these principles, which sound so strange and unphysical, but beautiful, artists and philosophers had them before us, that they actually govern the world. And when we try to make further advances in our knowledge, we hope that it's going to keep working. So now I'd like to show you how, by trusting beauty, we get to new ideas about what the future might hold for fundamental laws getting even more beautiful. So I mentioned we have three fundamental forces: weak, strong, and electromagnetic, that are the ones that are related to different kinds of color. And these are the substances that appear in our core theory of those forces. We have different kinds of quarks. These are their names, U and D. Left-handed, that's a technicality I'd rather not enter into here. But they come in three colors for the strong interaction and two different colors for the weak interaction. So this is a complete inventory of their fundamental properties for the strong and weak interactions. And if you know that, plus their electric charge, you know everything there is to know about how these guys behave. And there are left-handed quarks and right-handed quarks. Then there's the famous neutrino, electrons, and again, these also come in left and right-handed versions. But I'm not going to insist on the technicalities here. That would take quite a while to discuss. Just that you can honestly, in an honest way, write down our deepest understanding of the properties of the fundamental particles in this seemingly cartoonish inventory of colors and a few numbers. Now, actually, so as not to be lynched by my colleagues, and to make it fully honest, I should add a couple of more complications. First of all, there's another force, gravity. There's also an additional kind of substance, the Higgs fluid. And most embarrassingly, there's two repeats of this kind of structure involving heavier quarks and heavier so-called leptons, neutrinos, and electrons. So, having said that, I'm going to now ignore it. And let's compare that simplified version of the core theory, but not terribly simplified, that I showed you, to, you see there are different kinds of substances, there are several different kinds and different forces, and it looks kind of scattered. So it bears a kind of family resemblance to this thing. Whoops, sorry. Why is it going forwards instead of back? Oh. Okay, let me quickly recoup here. No. Oh. So that. No. Sorry, I've totally trampled on this joke. Okay, so that scattered inventory of the different substances, we had 6 different kinds of thing that with different distributions of color and different electric charge, of weak and strong color and different electric charges, should remind you of this. Kind of a scattered mess with 1 thing and 3 and 2 and so on. But if you have studied the mathematics of Platonic solids, or if you know about origami and making calendars, you might realize that what that is meant to be is a bunch of pentagons that will fold up to make a dodecahedron, and if you match the different numbers here and fold it up, you'll get a nice dodecahedron suitable for drawing a calendar on. So the question is, can we do something similar with the Standard Model, with the substances that we know about in nature with their seemingly very odd scattered pattern? Is there a deeper organization of them that would explain why they're lopsided in the particular way they did, but are, and somebody's cut the links and made this beautiful pattern into something that seems more obscure? Well, of course, I wouldn't be asking that question if I didn't know the answer. And let me very, very quickly indicate to you in pictures how you can have a beautiful, conceptually simple, mathematical, ideal object that leads to the scattered pattern of the Standard Model of that I showed earlier. So this is a table that has 16 rows and 5 columns. The 5 columns have pluses and minuses in all possible distributions, subject only to the rule that you have an even number of pluses. So you could have 0 or 2 or 4. And this is the same thing, but now written in a colorful form, where each column is representing a different color. So red here, then green, then blue, then yellow, then purple. So not by coincidence, the colors of the strong and weak interactions. And what I've done is every time there's a plus here, I've written a full circle, so that's a unit of positive charge. Every time there's a minus, I draw an empty circle. That's a unit of negative charge, the color charges of the different interactions. Now, we also had dangling those funny numbers, which weren't related to anything within the core theory, within our current understanding. The higher theory that leads to this pattern also tells you that those numbers are not independent of the weak and strong charges, but are generated by this formula. So we have this explanation. Now I've drawn the same table here. Unfortunately, because of the projection, you can't see the yellow empty circles here, but they're there. And the colors are a bit distorted, but I hope you can imagine this is meant to be red, green, blue, yellow, with where you see nothing, that's actually an empty yellow circle. Now, if you add equal amounts of all the three strong color charges, then you've done nothing. This is called bleaching rule. The different kinds of charges can cancel each other. So we can simplify this pattern by adding a unit of red charge, a unit of blue charge, green charge, and a unit of blue charge in such a way that we're just left with red and the others have canceled off. A bigger amount of red, but just red. And we can, similarly here, we can add an equal amount of yellow and purple. So we cancel off the negative and get a bigger yellow. And so forth, cleaning everything up. And then, magically, what you find is that these resulting assignments, which remember started from a very profound, simple mathematical idea of allowing all possible distributions of pluses and minuses with the constraint that you had an even number of pluses, and that special formula that told us that the electric charges are not independent of the strong and weak. Now we find that this table exactly matches the pattern of the known particles. So really, there's only one entity. They're all related to each other. They're all, and in the detailed implementation of this, where you can transform all of them into each other, there's only one force. Because the medium that's required to do that includes the strong fluid, the weak fluid, and the electromagnetic fluid, all together. Now, to get full value from this theory, so that it not only organizes substance, but also organizes force, so we've unified the substance in that way. We want to also unify the forces. We have to appeal to another idea. This is an idea for which some people got the Nobel Prize. That is that what you perceive as empty space is actually a complex medium with quantum fluctuations. And therefore, if we want to see what the basic forces look like, we have to correct for the effect of this medium. It's as if we're fish looking through turbulent water. We have to make a correction if we want to see clearly. So I've calculated how to do that. These are the different forces as we observe them. We'd like to think that they're all coming, that is the strength of the forces as we observe them down here. We'd like to think that if we look, stripping away the influence of the distorting medium, so look at shorter distances, which turns out to be equivalent to looking at higher energies, that those forces would be revealed to be all the same, that they would unify. So if that's the case, when we make the corrections, strip away the influence of the distorting medium, they should all come together. And whoops, doesn't seem to work. Almost, not quite. Well, what do we do in a situation like that? So many things seem to be coming together, and it almost works, but not quite. Well, if we listen to the advice of the philosopher Karl Popper, we could declare victory at this point. Karl Popper said that the goal of science was to produce falsifiable theories, and here we've produced a theory that's not only falsifiable, but actually false. But of course, that's not our attitude. If something deserves to be true, seems to be wanting to be true in nature, we want to help it along. We want to not falsify it, but truthify it. So maybe we have to use more imagination. Well, let's go back to the Taiji, the two fish. We've achieved, in a sense, a unification of the different kinds of substance and almost achieved a unification of the forces. They didn't quite come together, but almost. But even if we did that, we'd still have two different things: force and substance. In a really unified theory, we'd want to have just one thing. And each contains an element of the other. Maybe each could be seen as the other. We're getting used to this idea of symmetry, that there are different ways of looking at things that have the same content. Could that also hold for force and substance? Could it be true that you can make transformations that turn the force into the substance and the substance into the force and still have the same underlying description, same underlying valid description of the world? Well, it turns out that you can if you don't use the equations that we currently use to describe the world, but use a bigger set of equations. You have to use a bigger set in which there's an extra dimension of space-time. That should sound familiar. We're again expanding the concept of what space is and what distortions we can make in it. This extra dimension is the so-called quantum dimension. It's unusual in many ways. It's described by numbers that instead of satisfying the rule time with these extra quantum dimensions, then we can ask what would happen if you moved into superspace. Yeah, and I've been there. I did it. And what happens if you move into superspace is that if you were a substance particle, or technically they're called fermions, you turn into a force particle, a boson. If you were a boson, if you were a force particle, you turn into a substance particle. Exactly what we wanted to do to unify force and substance, because if it's possible, if it's possible to make those changes by moving into the quantum dimensions, and flipping over the quantum dimensions is as valid a description of the world as not flipping it over, then every force particle has to come with a substance particle to allow the structure to work, and vice versa. So, as I said, the equations we use now in fundamental physics don't have that property. They're too small. They don't live in superspace. But in our art of theory construction, we introduce additional structure so that we allow those kinds of transformations. That's called supersymmetry. To allow it, though, we have to expand the equations. That means the equations produce for us more stuff. That means we have to revisit the corrections that we make in order to notionally see down to much shorter distances, to see whether the unification occurs. So, with the stroke of a pen, we can make those changes. And this is what happens. When you include the new kinds of materials, the new kinds of the force partners of all the known substance particles and the substance partners of all the known force particles, they modify the corrections, and the observed strengths of the different interactions nicely flow into a unified underlying one force. And as a special gift, gravity, which we've sort of been blithely ignoring in this unification, in the world of elementary particles, it's actually a very fine approximation to neglect gravity because it's inconceivably weaker than the other forces, inconceivably feebler at known energies, but gravity gets strong much more rapidly than the other guys change, and at the last minute, from way outside the known universe, it comes in to unify more or less with the others. So this was unanticipated, but comes out of the calculation. And it's very encouraging because it seems to be something we're getting out more than we put in. That's always a sign you're on the right track. And it seems that all the forces can come together if we have the supersymmetric particles. And now it's up to experimenters at at the Large Hadron Collider, who are investigating this question to see if these bold extrapolations, trusting beauty, correspond to reality this time. Okay, so I've mentioned many, many ideas. I hope I've given you a sense of the beauty of our fundamental description of nature, how much we've achieved, and how we can use it as a guide to what we might expect in the future. If you want to see all this in more depth and much more, coming in July is a beautiful question where all these things are explained in much more depth than I could do in a brief lecture like this, and put in historical context going back to the ancient Greeks. And this is the cover. You see there's a peephole here. And wow. Okay. Yeah. We're losing a lot of the images here. This should say Finding Nature's Deep Design. And if you want to find nature's deep design, what you have to do is open the cover. And this gives a first hint of, or a metaphor, if you like, for the fact that nature doesn't disappoint. Okay, thank you very much.
Thank you, Frank, for a beautiful talk. So we have the chance to ask a few questions. I think there are microphones that will be coming around. So if you would like to ask a question, please raise your hand and we'll get you a microphone.
Okay, we can start here.
And please try to keep them short so we can get through a number of questions before our time runs out.
The microphone's coming.
When the Higgs was discovered at the weight that it was, why did that discourage so many people on supersymmetry?
The question is, when the Higgs particle was discovered with the weight that it has, why did that discourage many people about supersymmetry? Because they were silly. In fact, it's very encouraging for supersymmetry. The Higgs particle, a very wide range of masses. Technically, it could have had a mass, theoretically, anywhere from 10 GeV, that's the measure of mass in particle physics, up to several hundreds of 1,000 GeV, say. Supersymmetry predicted that its mass should be roughly between 100 and 150 GeV. So that was a very non-trivial prediction. And it's true. Now, some people got greedy and wanted to push the models, which have various uncertainties, very hard. And when you push very hard, it's difficult. The most straightforward models, minimal models, predict a Higgs particle mass which is slightly less than what's been observed. But to me, this is straining at a gnat. The big picture is it's very encouraging, and this picture of unification, which relies on supersymmetry, is much weightier evidence for it than that over-interpretation is evidence against it, as far as I'm concerned. Yes. Maybe we'll try to move.
So you're expecting we're going to find supersymmetric particles when they
Yes.
charge up LHC?
I hope so. I bet on it. That's right. So was that a question? I mean, what?
What happens if we don't?
If we don't,
Yeah, they're all going to go down the drain.
I'll lose some bets. I bet that by the year 2020 we will have evidence. We'll see. It's not up to me, but if it were up to me, it would really be a beautiful thing. And as I said, nature, beauty has been a wonderful guide to the laws of nature so far. I think the laws of nature are considerably more beautiful in two different ways if we have this supersymmetry. One is supersymmetry itself enables us to unify force and substance. The other is that quantitatively, the unification of the forces, which seems to almost work, and would really, and certainly works at the level of organizing the census of substance in a very compelling way. That would work quantitatively in a very impressive way in detail, if and only if we have the particles that supersymmetry predicts. Yeah, I can't.
Yes,
I can't see very well out there.
I'm not a physicist, not a natural scientist.
That's all
I'm
right.
a social scientist.
You're an artist? Oh,
So to my understanding, the lecture seems to be like a political allegory. Now, I was trying to understand it in the political side of it.
the political side?
Political side of it, yeah. Is it which one is substance? Which party would be substance? Which party would be force? And what would be the symmetry to make the two-party system work?
Oh, two
Or are you trying to say that we need three forces? That means do we need three-party system to make it work? Thank you.
Well, I think it's beyond the resources of physics to turn Republicans into Democrats and vice versa, if that's what you're asking for. But I'm not sure what the question is. Maybe I'll just play it straight. Oh, so substance particles, also called technically fermions, are the kinds of particles that have the properties you normally associate with substance. That is, they repel each other by the so-called Pauli exclusion principle. They don't want to be pushed together. They can't be annihilated except in pairs, so they have a certain kind of permanence to them. Whereas the force particles can be and are often in states where many of them are doing the same thing, so they exert a big influence, also known as a force, like electromagnetic forces. and they sort of come and go. A light can be easily emitted and absorbed, so they have more the yang kind of feel to them. By the way, another eerie coincidence is that the physicist who discovered this way of creating theories is named Yang. Frank Yang, and the theories are called Yang-Mills theories. Yes. So physicists, it's amazing. Well, that plus the fact that people rather whimsically talked about color charge and the strong interaction, and then it turns out to have properties that are very reminiscent of perceptual color. These are things that are like Twilight Zone.
Frank, I think there's one back there.
Yes.
Okay. So I've had this question for a while now, and I haven't gotten anyone to really answer it satisfactorily. So I decided to go for the top because it's a physics question. It's very interesting. So on a macro scale, like the reason, like I know that atoms don't collapse into each other because the electrons repel each other, right? And the reasons
Well, that's part of the story, yeah.
yeah. Well, atoms are mostly empty space, and so like they could, but the electromagnetic force keeps them apart. But in something like a neutron star, for example, where you have nothing but neutrons, and there's no electric charge, what keeps those neutrons from collapsing into each other, into just like some space that like all these neutrons like stacked on top of each other in 3D space? Why doesn't that happen?
Okay, well, those are questions that have rather elaborate answers, but let me make a little start on it. The real answer is you should buy the book. Because I do answer those questions. So the reason atoms don't collapse is not because electrons repel each other. For instance, the very simplest atom is hydrogen, and it consists in a proton and an electron. Not two electrons, just one electron. So it's not a question of electrons repelling each other. It's the electron should, according to the laws of classical physics, be attracted right into the proton, and the hydrogen atom should collapse. This was a great paradox at the beginning of the 20th century when people first realized what the structure of atoms is, that there are such things as electrons and protons, and they're organized in a kind of planetary-like system. Niels Bohr famously solved that problem sort of by fiat. He said, that's the way it is. It's quantum mechanics. You have something called stationary states, and in what I think is arguably the greatest paper in physics, and maybe in all of science, in the 20th century or ever, he just assumed it and gave some rules for what the allowed orbits of electrons are that forbid it to fall into the middle. So he gave the so-called quantum rules. That was the beginning of the quantum mechanical understanding of matter that roughly 10 years later gave birth to modern Schrödinger equation and modern quantum mechanics. Quantum mechanics is not something you could realize rationally as a consequence of earlier laws of physics. It's different, and it's a break, and there's no simpler way to understand it, because that's just the way it is. Okay, so if you ask me for an intuitive understanding of why atoms are stable, there is no quantum mechanics. And now neutron stars bring in another idea. What keeps neutron stars from collapsing. Quantum mechanics comes in, but a different aspect of it is important, which is that it has to do with this property of substance particles, or fermions. Fermions obey something called the Pauli exclusion principle that says they can't occupy the same state. So if you have neutrons or many, many quarks, which make up the neutrons, they can't occupy the same state, which means they can't collapse. So again, it's a quantum mechanical phenomenon that keeps it from going.
So we have maybe time for one more short question. Is there one over
If
here?
it would, you know, if neutron stars were made out of photons, they would collapse. Right? Yeah.
I'm not a physicist, so you'll have to excuse me.
You're excused.
All right. When you energize protons and at very high speeds, and when two protons approach each other around 2 diameters, you get the strong force takes over and they fuse. How does that fit into your discussion? In other words, what's happening?
That's the strong interaction. And as I mentioned, it's based on kind of electrodynamics. It's very similar conceptually to electrodynamics, the theory that Maxwell discovered, but it's electrodynamics on steroids, because there are 3 different kinds of charge, not just one, and 8 different kinds of photons, the gluons. It gets very, very complex to describe how all those things affect each other. It's only recently, with the help of massive computer simulations solving the equations, that people have really started to be able to explain on the basis of QCD how protons are assembled from quarks and what happens exactly when you bring 2 of them together. I'm not sure exactly what you're asking, but it's complicated, that's all.
Okay, that's it. Thank you so much for coming. And thank you, Professor Wilczek, for a great talk.